In this video, we're going to go through an example with arc length and go through some other information that's actually really important in relation to arc length. This curve we actually saw last week in an example in the videos there. And per our previous experience in the video where arc length was explained, we know that to compute the arc length, I actually need to compute the derivative vector, which is to say, take the derivative component by component, and so doing that I get 2t negative sine t squared, and then 2t cosine t squared. Okay. And then it said, okay, compute the length of it. Okay, length of the derivative vector. You can pause the video and double check this on your own, but I got 2t. Okay, so then the length of the vector x here is going to be the integral from 0 to root 2 pi of 2t dt, and then some magic happens. Do the integral on your own, and you get 2 pi. That's kind of fun. Okay. You're going to find that computing arc length can be one of the more annoying tasks in your day. Okay. So just be ready for that. You might have to use Wolfram Alpha Pro to help with the calculations on occasion. Okay. Now on to the notes part here. So that was our example. This theorem is actually quite lovely. And so what it says, I'll let you read the technical language here, but if you have two parameterizations, right, you have x and y with different bounds, etc., and they do have a smooth parameterization of a curve, then the arc lengths are the same. So parameterization of the same thing doesn't matter with arc length, okay? And guess what? You get to prove it in your professional problem this week. Have fun! All right, some other notes. First, it's a little bit of notation here. Whenever we are computing arc length, we actually say it's the arc length of a curve C. But in practice, when we're computing it, we compute it as the arc length of our parameterization for that curve, right? So just a heads up on that. Okay. Next thing is that if you have a curve that might be, I don't know, piecewise continuous, something like that. Okay, so you have kind of three junctures here. You have first curve, second curve, third curve. To find the arc length, guess what you do? Okay, I'm gonna start out our notes. So for a piecewise smooth curve, okay, well, hopefully you've had some time to think about it. For arc length, you just find the arc length of each piece and add them up. Of each piece, and add. Okay. That probably wasn't as surprising as what you might have imagined. And then, like I said previously, computing arc length integrals can be kind of tough. So here in this graph, we notice that, or for this parameterization, we notice that it is a parameterization of an ellipse. So let's see, we go 3 in the x direction and 2 in the y. So it's an ellipse, and I'm going to do my best drawing ever. Well, we'll move that tick mark. We'll call that 1, and that'll be 2. So it's an ellipse, and it's parameterized in this fashion from 0 to 2 pi. And so finding the arc length here seems pretty straightforward, right? So I would go through and compute the derivative vector, and I get negative 3 sine t comma 2 cosine t. Okay, and then I compute the length of x prime of t. Well, okay, this is going to be a little less fun. This is 9 sine squared t plus 4 cosine squared t. And then I need to take the arc length of this. Okay, so then 0 to 2 pi of the square root of 9 plus sine, not plus times, 9 sine squared t plus 4 cosine squared t. There might be a little simplification you could make. For example, I think, okay, you can confirm, I think you can write this as 4 plus 5 sine squared t. But beyond that, we have to use Wolfram. Or look back at famous mathematicians who have done this. I think these are actually called elliptic integrals, and there's special formulas used to compute those. But generally, computing arc lengths is kind of tough because of that square root in there. Okay, and that's the end of this second video. So we've gone through the idea of arc length and some examples and notes related to them. In the next video, we'll actually talk about it as a function. Stay tuned.